All right, hello everyone, and welcome to our lecture on Chapter 8. This is the last chapter that we have on symmetric key cryptography, and it's going to be covering stream ciphers specifically. The previous chapters that we focused on were all about block ciphers and how they work. And we had the different modes of operation, the different kinds of protocols that we had, AES, DES, different structures. But we're going to come out of those schemes now, and we're going to focus on stream ciphers. Now, as you recall, stream ciphers are mostly, defined as this structure over here. So we have our plain text P, um, and we have a key here that is going to be exclusive ORed with our plain text. And from that, we're going to get our ciphertext. So there's not much structure in here, in terms of operations. The only operations happening is the exclusive OR. However, there is one important piece here that plays a vital role in the security of a stream cipher, and that's this guy. That's this key over here. And as you recall, in the previous lectures that we had, I mentioned briefly that this key is supposed to be as random as possible because this is this piece here, this key is literally hiding all the information that you can have in your plain text because it has to be random enough to flip to flip randomly some bits of your plain text. And so if the adversary sees the ciphertext, he doesn't really know which ones were flipped and which ones weren't. In other words, from the perspective of the adversary, there's a 50-50 chance that a bit could have been flipped or could not have been flipped, right? Meaning that you have maximum amount of uncertainty. So that's what we're going to be focusing on in this chapter. The entire chapter, this chapter 8, is focused on this vital piece over here, the key. And how do we generate keys? How do we generate random bits to be used as a key? What are the different methods? Some of the tests that they have to pass in order to be considered safe to be used in a stream cipher. And this is basically what we are going to be covering. So let me just clear the whiteboard over here, and then we will move to the slides. So like I said, we're going to be talking about random bit generation and how they're going to be used in stream ciphers. So basically, when we talk about random numbers have a very special place in cryptography because a lot of what we do is based on randomness. And specifically, we have key distribution and reciprocal authentication schemes. Like I said, in our discussion, not only on stream ciphers, but about block ciphers, the keys have to be random bits. You can't have a specific key to be used in a encryption scheme. Otherwise, the scheme would be broken. It has to be a random string of bits, so it's hard for the adversary to find it. One of the other things that we have is the session key generation, which basically, is again sort of touches on the topic of keys that are going to be used in AES and DES and any other protocol that you can think of, symmetric key protocol. We talked last week about some stuff on RSA. We introduced the algorithm. So generating the keys, if you recall, the public key and the private key is again another topic where random numbers come in and how to generate those random numbers. And of course, in this topic, we're going to be touching on where generating a random bit stream for symmetric stream encryption, or basically a stream cipher. So you can see that when we talk about random numbers, most of what we do in cryptography is actually built on generating random numbers. And that's why they have a very, very special place when in cryptography. Now, there are certain properties that a random number, or a sequence of random numbers has to have in order for it to be called random. First of all, it has to have randomness. And the second property that has to have is supposed to be predictability. Now let's go in depth and see what these terms actually mean. What does randomness mean, and what does unpredictability mean? So when it comes to randomness, what we mean is that the sequence is supposed to have a uniform distribution, and it has to have independence. Now, what we mean by uniform distribution is that if you take a long enough sequence of randomly generated bits, and here because we're mostly dealing with binary numbers, we're going to talk about bits. We're not going to talk about integers. It's going to be zeros and ones. So the distribution of zeros and ones should be pretty much equal. So in a long enough sequence of bits, if I have, say, 100 random bits, about 50 of them, roughly 50, should be ones, be 0, and around 50 should be 1, right? And it makes sense why we have this property, because you don't want one bit being more than the other, because this will reduce the uncertainty that an adversary has in terms of finding the bits that were flipped. He'll know that because there were more zeros, so there's a chance there's more of the bits of the ciphertext are exactly the same as the plain text. And that's not what we want. We want to have, roughly 50 zeros, roughly 50% 0, 50% 1, so that the adversary has maximum uncertainty towards the values here in the random bits that we have. The other thing is that it should the sequence should have independence. Now, what does that mean? It means that each bit, or each subsequence of bits, should be independent of other bits or other subsequence of bits. In other words, if I take this bit over here, let's say I take this bit over here, whatever this bit is, it should not affect what this bit is, or what this guy is, or what anywhere something over here is, right? All of these bits should be independent from each other, right? And same goes for subsequences. So if I have, say, if I take this subsequence of bits over here, whatever this thing is, let's say it's 1011, it should not affect what this subsequence is, or what this subsequence is, and so on. You get the idea, right? These should all be independent from each other. And again, the reason is pretty obvious. And it's pretty much that if the adversary knows that these are not independent, he can pick out he can extract information from the sequence, and therefore he can figure out what the plain text is from the ciphertext. So when we talk about randomness, we're basically talking about these two properties: uniform distribution and independence. Now, if we go to unpredictability, it means that the successive members of the sequence are supposed to be unpredictable. meaning that if you have say a string of a string of bits, 100 random bits, and you know that what these 100 random bits are, knowing this should not give you any information about what the 101 bit is going to be, right? So every bit should be unpredictable from any sequence of bits that you have prior to it. Now, what we have basically is something we call true random sequences, right? So basically, in a true random sequence, each number is statistically independent of other numbers in the sequence. And so, by definition, it's unpredictable. However, implementing true random numbers or generating true random numbers is not very efficient, and it brings more complexity than you would think. So that's why we actually don't have something called true randomness. We opt for a lower definition or a lower standard of random bits that we're going to get into in the next slide. But this lower standard still satisfies what we are going to be achieving with these bits in a stream cipher or in a key generation or any other application that it comes down to. Now, that lower standard is called pseudo-random numbers, right? And basically what it means is that they're not truly random. They're generated using a deterministic algorithms. And so the output we know is not going to be statistically random. So every bit is not going to be completely independent of the one previous to it. However, there are tests that every random or pseudo-random number generator is supposed to pass. And if it does pass those tests, then we can say that this pseudo-random generator is good enough for our application. We don't need to actually implement a true random number generator and go through all that complexity and all the costs that comes with it. We can just opt out for a pseudo-random one, and we know that it will be good enough for our application. So in this chapter, we're going to be talking a lot about pseudo-random number generators and how they're built. We're going to be going into some of the examples, and you'll get an idea of how pseudo-random number generators work in the cryptography world. So in terms of true random number generators, pseudo-random number generators, we have this diagram here. So you can see that when we talk about a true random number generator, we have a source of randomness, right? And this is a source of true randomness, meaning that you can it's something that's completely random. For instance, the clicks or the places you click your mouse on a computer screen, or the keystrokes on your keyboard, or random instances of time of your computer. And because the source is already random, you can just easily convert that to binary, and that'll be your random bit stream. For a pseudo-random number generator, we basically have a deterministic algorithm, and that algorithm, we feed a seed into it. So this seed is something random, and I recall talking about this in the previous lectures, where if this seed is shared between the sender and the receiver, they can both determine that sequence of random bits. And this is actually how it works. The seed is fed into a deterministic algorithm. And the reason we call this deterministic algorithm is because if you give it the same input, it'll give you the same output. If you give it, if you, the sender, gives it a certain seed and get a output, and the receiver gives it that same seed, that receiver will get the same output that you as the sender got. And usually in the deterministic algorithm, we usually take the output and then feed it back in to the deterministic algorithm, sometimes to bring in more randomness. Sometimes it works without us having to feed the pseudo-random bit stream back into it. There's different variations, but this is generally how it works. Another notion that we have with random bit generators is a pseudo-random function. So in this function, we basically not only have a seed, and not only are we sort of providing a feedback loop with the algorithm, we have some specific values that are constant that we're feeding into it as well. So you can see, it's a multi-input algorithm, and it gives us a pseudo-random value. So it takes all these inputs and it gives us one value. It's not like a bit stream or anything. It's a random value that we can then use, either convert it to binary or do something with it, and then we can generate a pseudo-random bit stream with it. So this is basically a pseudo-random function. This is basically a pseudo-random number generator and a true random number generator. Like I said, most of this topic, about 90% of it, is going to be based on this PRNG, or the pseudo-random number generator, and we're going to be going into the structures of it and some of the tests and some examples of pseudo-random number generators. So if we move to the next slide, so this is basically, the true random number generator that we have. And like I said, some of the examples that we have for true random sources are keystroke timing patterns, mouse movements, or where you click the mouse on your screen, instantaneous values of the system clock. These are all, true sources of randomness. Then you can just apply a binary conversion to it, and then that'll be your random stream of bits. However, one of the problems with this, like I mentioned, not only is the complexity and implementing it is hard, but the receiver also has to have, the same keystroke timing pattern, the same places that he clicked his mouse, or the same values of the system clock should be sampled in order to get the exact same output. If one of these is a little bit off, then the sequence that the receiver generates is not the same sequence that you as the sender had. And so you will not be able to decrypt the ciphertext and get the same plaintext. So the receiver will decrypt to another plaintext, and they will have no way of knowing that they actually made a mistake. So that's one of the problems with true random number generators. Every input to that binary converter has to be the same. Whereas in pseudo-random number generators, it's only the first input that has to be the same. After that, the deterministic algorithm will work in a way to generate the same output. So if we move to pseudo-random number generators, like we said, you basically have a seed that you put into it, and from there, the output stream is generated. And one of the things that we have to know about pseudo-random number generators is that we never actually keep the structure of the pseudo-random number generator a secret. It's only the seed that is kept secret, right? Same way that when we were analyzing cryptographic schemes, we didn't really keep the algorithm a secret. We didn't keep step 1, step 2, step 3 in our encryption scheme a secret. We gave that to the adversary. The only piece of information that we kept secret was the key. The same thing goes here for pseudo-random number generators. If we want to see if they are actually a good source of randomness, we don't keep the deterministic algorithm secret. That is known by everyone, including the hacker. The only thing we keep secret is the seed. And the question that the hacker has to answer is, how hard is it for him to find the seed if he's given a output of that deterministic algorithm? Now, like we mentioned in the picture, there are two forms of the pseudo-random number generator. There was one with the deterministic algorithm, and there was one with the pseudo-random functions, right? These ones, like I said, there's one value that comes out of it, just a single value, and then we convert that to a binary. So they're good for, using as like keys in AES or DES or any other symmetric key encryption, and also as nonces, if you recall when we were talking about, modes of operation of symmetric key encryption schemes. One of them was like ciphertext feedback mode, which had a nonce. This is a good place where you can use a nonce. And yeah, but if you want like a pretty long sequence of bits, the pseudo-random number generator itself is the best one to use, and not really a pseudo-random function. So if we move forward, like I said, the basic requirement for a pseudo-random number generator or a pseudo-random function is that the adversary who doesn't know the seed cannot determine what the random sequence was. And so there are certain requirements that a pseudo-random number generator has to satisfy before it can be actually used in an application. And the areas that it has to satisfy those requirements is basically randomness, unpredictability, which we already had before in terms of, random number generation, and also characteristics of the seed, which we will get into shortly. So in terms of randomness, we've already covered this, but we'll go over it again. Basically what it means is that the generated bit stream needs to appear random from a hacker's perspective, even though it is actually the output of a deterministic algorithm. Like you, the sender, and the receiver know that the algorithm is deterministic, and the hacker also knows that. But the output is so random that he cannot find any information about what the seed or what the input to the algorithm was. Now, there's no single test that can determine if a PRNG or a pseudo-random number generator generates numbers that have the actual characteristic of randomness. But there are tests that we can use to actually check these. For instance, the NIST SP 800-22 are tests that we can carry out so that we can find out if there are three characteristics that a random output should satisfy. For instance, uniformity. In other words, is the distribution of zeros and ones 50% or close to 50% for all of them? Scalability and consistency, which we'll go to a little bit further on. So, like we said, there's not just like one test that you can run, but there are a series of tests that establish, three characteristics, uniformity, scalability, and consistency to see, if the randomness characteristic of a pseudo-random number generator is satisfied. And I'm going to pause the video here right now. This will be the end of part 1, and then in the next video we'll continue with the rest of the slides.